Hi, welcome to my class. My name is John McFetrich, and I'm just going to talk to you about artificial intelligence. And the question is, should we remove the I? Well, quite frankly, I have no idea. But I want to just share with you some of the things I've been learning in the last year. I spend a lot of time on YouTube and just learning as much as I can about this fascinating subject. And I don't pretend to have absolute answers, but I can just share with you some of the things, interesting things I've been learning. Anyways, so I've been involved with technology since I was a kid, and my first days were on IBM mainframes. And back in those days, we would have these large machines that would fill. Well, in the case, the first machine I actually worked on filled it in 2 floors, and the thing was actually the memory units were so big. They were one of them caught on fire, and I happened to be standing beside it. Pretty scary, especially when the alarm went off. And but now all this processing power we can put on a watch. So what I want to discuss with you is a little bit. We have to look about define intelligence, because that's the question we're asking. And a brief outline of where we are now, and some of the problems with these solutions. And then we're going to look at an interesting alternative from Numenta and Jeff Hawking, the 1,000 Brains project. And so let's get started. History, of course, this thing, AI is really nothing new, although it seemed like it came from nowhere 3 years ago, but it's been around since the 50s. And in 1956, it was a term that was coined by John McCarthy at a Dartmouth College seminar. And in the 50s, there was a lot of interest, and there were the earliest AI programs. And at this time, Alan Turing came up with his Turing test, which was to determine a machine's ability to exhibit intelligent behavior indistinguishable from that of a human. Well, of course, we haven't reached that stage. But machine learning languished for many years, but it began to there was a resurgence in the starting in about 2010, and particularly about 2013, 14, with image processing using neural nets. And there was a contest up in Toronto, and which was won by a team using AlexNet, and AlexNet was an early neural net that was put together for this image processing, image recognition, and by a team that included, or at least it was overseen by Jeffrey Hinton, the founder, that's called godfather of AI. And one of the astute organizations watching this event was NVIDIA. And NVIDIA gave them one of their GPUs, and they were able to use that GPU to run away and easily win the contest. And at that point, from then on, we began to see more and more image face recognition. And I'm sure many of you who've been using Facebook for 4 years will remember that the little squares that would go around the people in your photos. Now, and a big event happened in 2017 when there was a paper published called The Transformers, Attention is All We Need. Now, this was huge. As much as so, we got pretty good with image, but we still were languishing with text. And this this all changed, but more on that later. And of course, we were part of the reason that AI was languishing was the lack of compute power. Well, that changed, and particularly as we got the GPUs and the graphics processors, and of course, and the prominent player there is of course NVIDIA, and more on that later. And then in about 2-3 years ago, came to see everything was transformed when ChatGPT was released. And so first of all, we have to define is AI. What does AI mean? AI, well, one definition, the capacity of computers to simulate human intelligence. But of course, that begs the question, what's intelligence? And so the intelligence is hard to encapsulate in a single definition. And it's interesting how a brain made of simple cells called neurons creates intelligence. And this is a profoundly interesting question and somewhat remains a mystery. We're learning more and more, and we're going to go into this likely later on in the talk. Because we're going to be looking at the Thousand Brain Project, a new theory of intelligence by Jeff Hawkins. And he says that intelligence is the ability of a system to learn a model of the world. Much more on that later. This years ago we had John Locke who said intelligence is a general learning ability, and this is opposed to what Darwin said, which he believed intelligence is a collection of task-specific skills honed by evolution. Interesting difference. Now, we're going to be looking at Francois Chalet's ideas later too, but one of the thoughts he has is we have to differentiate between skill and intelligence. And intelligence is a process whose output is skill. And displaying skill any number of tasks does not show intelligence. So if you get, in this case, we have, the road that we drive on is the result of the road building process. And the road building process is going to contain the intelligence. The road is just the means to get from point A to B. And the skill, when we get something like a computer can play Go, well, it's a skill. It does have a really good skill, but it doesn't mean it is intelligent. We have to be careful. But important, wrapped up in this, is the idea of generalization and abstraction. So part of intelligence is, this is again the thoughts of Francois Chalet. Chalet was one of the top tech people at Google, and he says part of intelligence is mining your experience of the world to identify bits that are repeated, and that we want to extract these atoms of meaning, and we're going to call them abstractions. And then we're going to use these to make sense of new situations, and particular new situations. And so he says to be truly intelligent, we must be able to generate abstractions autonomously that can solve novel problems. And if we're able to do this, then we're on the path to AGI. And AGI is the holy grail. The AGI is the artificial general intelligence, where the software is able to master new tasks with very little experience. So these are the ideas behind intelligence, particular generalization, and what it means to move towards AGI. So we need to move towards decisions. It's going to learn without being programmed. because it's going to learn, it's able to learn from the data. So the idea is to allow the computers to identify patterns, relationships, and trends in the data and make predictions. So it's looking for it wants to infer relationships in the data, and it's going to do this by three stages. We're going to have training is the core machine learning, is the idea that a system can be trained using a set of data. And during this training phase, the system attempts to learn patterns or structures from the data. And then from this, it's going to build, but we're going to look deeper into training soon. Then from this, it's going to build a model. And once the system has been trained, it creates a model. And this can be thought of the system's learned understanding of the data it was trained on. And from this, it can start to, we can begin to make queries, ask it questions, and hopefully get answers that make sense. Now, a neural net is a subset of machine language loosely inspired by the structure and the functioning of the human brain. And I say loosely because our ideas, neural nets the idea of a neural net has been around for 30, 40 years. But and we haven't much changed how the operation of these software neurons function over that time. And however, our understanding of how neurons work in the brain have changed a lot during that time. But these are capable of learning complex patterns, and the foundational architecture and the learning mechanisms for our large language models and like ChatGPT. Now, as a simple example of how a neural, I want you to understand the basics here. We're going to drill down a little bit into the weeds because I want to show you that we're dealing with something that is math, particularly linear algebra, and there is no magic here. And it's just a bunch of math that is put together to be able to infer, using that to infer and make decisions from the data in these models. So with a simple example is we're kids, we want to, that was a while ago, we want to decide whether we want to go to the playground. And we've got three factors. One, is it sunny? Are our friends going? Have we done our homework? And in this case, we're gonna say it's not sunny. Now we can't assign. Computers only know both numbers, so we're going to assign 0 for false, 1 for true. So our friends are going, and we haven't done our homework. Whoops. Well, we probably shouldn't be going to the playground. However, and now we can give these things different importances. So the fact that it's not sunny, we can give it a weight of 3, and we call these weights. And if our friends are going 5 and homework 1, well, I think I would have a talk with a kid who assigned those weights. However, so we're all these inputs, and every input is going to go into every neuron in the next level. So, and we're going to add up these values and compare it to a bias. In this case, we're going to assign 6. And so we calculate our sum, which is the 0 times the 3, the 1 times the 5, and 0 times the 1, which is 5. And then we compare that to 6. Well, we don't go. So, and now we can play around with those weights And if we can go in, we can change this to 3, and this is going to, and then our friends are going, it's going to be more important, so we make it 7. And then homework's still low, 1. And if, in this case, where our sum comes to 7, which of course, now we go. So this is a simple example. However, it's really, this is how what a neural net does at its very basics. And as we adjust these weights, this is a process we call training. So in the case of this is from a simple case, we can take and we can put more hidden layers here, and these are the way we get emergent powers start to appear, particularly as we make these bigger. And as we add more of these, this is what we call our deep learning neural net. So this is a simple neural net. So the inputs, and we have multiple hidden layers, and we make decisions in here, and out come these outputs. Now, a large language model is a form of a neural network, and things like ChatGPT are LLMs. Now, these are tailored for natural language processing, and this is what made these things so successful, because we can talk to them almost like we're talking to our friends, and they're very conversational. In fact, and it almost seems as if you're carrying on a conversation with your friend. Now, they're big, they're large, they can be trained on billions of words. And of course, this is what ChatGPT is. Now, but again, I want to emphasize that I'm not going to show you anything about how to use ChatGPT. I want to show you how the inner workings of it and how it is created, or how it works, more about how it works, and so that we have that understanding of maybe it's not, not talking about intelligence, we're talking about just statistical analysis here. And the training is part of the key here is how these networks are trained. They go out, the first thing they do is, at great cost, they go out and they crawl every website in the world that they can access. And of course, the largest one is Wikipedia, and they pour that into what will become the model. And at first, it's in the raw form. It's unsupervised training. It's just going to be looking for relationships and then raw data. Now, and trying to find patterns. However, of course, at this stage, if you start to ask a question, the answers are pretty bad. So then we start we start a couple more forms of training, and these are supervised training. When we bring in humans, and the human contractors are going to play the role of both a user and the ideal chat box. So they're going to train the model to have human-like conversations. And then this is entered into the model. And we keep adjusting these weights, which we looked at in our simple example, and we adjust the weight. And this is very time-consuming and very costly. And they have thousands of contractors, thousands. And it's super expensive. So, but in the end, let's just, this Grant Sanderson has developed these, I think, outstanding videos, and particularly, he has some great visual tools. And let's just have a quick look at how Grant explains this.
Here we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watched the last two videos, or if you're just jumping in with the appropriate background, you know what a neural network is and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons. And I've been showing a network with 2 hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost.
So the point is, I think this is a beautiful job, and this is his own visual tools that he's using, and so he's applying these cost functions as pure math, and to calculate these gradient descents. And in fact, it's using derivative math the same way we learned back in probably first year university.
Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it.
So, pure math, pure derivatives, and it's expensive. Now, so, and of course, ChatGPT, the result of all this training is one of them was, of course, ChatGPT. And this is the super successful large language model from OpenAI. OpenAI, and of course, has always been in a partnership with Microsoft, and they had up to 2 million users. Of course, 100 million came in the first 9 months, or the first month, and it's expensive, and there's no way around it, and super compute intensive, thousands of GPUs that are needed to train this, and it's hard to keep up to date. They patch it on a regular basis whenever they find inconsistencies, and they find they want to align the model. Align just means to remove some hallucinations. Of course, it hallucinates, as we all know, and this is one of its downfalls. And it's up to date to about August 24th. And of course, if you have the advanced ChatGPT, you can go out and it can search the web. It's huge. This thing has 1.8 trillion parameters or weights. Remember those weights that we looked back at in our simple example. And there are 50 billion. Oh, wait a minute. Let's see, my captions are on here. Well, I'm going to leave them on. Now, it has so much data that it would take a person reading 1,000 words per hour 1,000 years. There's some, and the name is ChatGPT, and the generative just means that it's generative AI. It's going to generate new content, and from the model, and including images, where like with DALL-E does an amazing job. I'm super impressed. And of course, it's pre-trained on all this gazillions amounts of data. But the key word and what makes all this work is a transformer. And now we're going to dig more into, because again, I want you to have some idea of how this works so you can see really it's just statistical models, it's statistical processing. That's all it's doing. So attention is part of this transformer, and it addresses the following problem. I swam across the river to get to the other bank. Or I've got another sentence, I drove across the road to get to the other bank. Well, what is bank? Well, bank can be a financial institution, or it can be a sloping raised land. And most of us humans are able to take a look at this sentence and immediately grasp its context from the words river and swam in the case of the river bank, and in the case of the financial institute, we're going to gather understanding from drove and rode. And this is the same thing this attention mechanism is trying to do, is trying to gather information. It's trying to put this bank into gain context from the words that have gone before it. And the way it does it is with these, and again, I just want to show you some of the math behind this to understand it. The word embeddings, it's going to, with these word embeddings, is that we're going to build up this vector, and a vector is just a list, and the words in the English language, there's about 20 to 30,000, and for every word, it's going to have an entry in this list. And so I have, for instance, the word house. It could be at entry number 1000. Because the computer doesn't know anything, they have to convert the words into numbers, into digits. And so this is what our word embedding is doing. And these embeddings by themselves, each enter is another vector of thousands of entries, in the case of ChatGPT, up to 12,000. And each representing a different aspect of the word's meaning. Just as you might describe a house by its characteristics, like type, location, bedrooms, bathrooms, that the values in an embedding quantify a word's linguistic features or semantic meaning. Now, just to try and explain this more, here's a case that I took from Louis Serrano's the attention mechanism in large language models. He has this quiz here. He's taking these words, apple, banana, strawberry, cherry, blah, 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 and down to bicycle, truck, and assign them XY coordinates in this vector space. So this XY coordinate is a vector space, and the term often used in large language models. So in here, so the words that are like they're fruits, they're going to group, they're going to cluster more closely together. So the apple, bananas, and strawberries are going to be in this little group. Things like the bicycle, the truck are going to be down here. And so where would you put the word apple? Well, I think it's fairly obvious. It's right there. And but now we're going to change our scenario. We're going to make it slightly different. We're going to have the strawberries and blueberries and, I don't know, whatever, tomatoes up here in the right-hand coordinate. And down here, laptops, Androids. Now, and this is kind of a cluster of computer thingies, and this of fruits. So now, where would you put the word apple? That's more difficult. So now again, we're going to go back and take a look at a couple of really good videos that Grant has done.
Mind. The goal of the model that you and I are studying is to take in a piece of text and predict what word comes next. The input text is broken up into little pieces.
So it's all about predicting the next word in the context of what's gone before. This is the name of the game.
Pieces that we call tokens, and these are very often words or pieces of words. But just to make the examples in this video easier for you and me to think about, let's simplify by pretending that tokens are always just words. The first step in a transformer is to associate each token with a high-dimensional vector.
Now these are those embedding vectors that I talked about earlier. And these, in the case of ChatGPT, are up to 12,000 different values here. And these can be just, nobody is really sure what they assign, but they just give semantic meaning to these words.
What we call its embedding. Now, the most important idea I want you to have in mind is how directions in this high-dimensional space of all possible embeddings can correspond with semantic meaning. In the last chapter, we saw an example for how direction can correspond to gender, in the sense that adding a certain step in this space can take you from the embedding of a masculine noun to the embedding of the corresponding feminine noun. That's just one example. You could imagine how many other directions in this high-dimensional space could correspond to numerous other aspects of a word's meaning. Context I want you to have in.
So each word is going to add new attributes and new semantic meaning and influence the last word in the last word in the input. And this can be up to 8,000 characters back that are going to influence and to slightly modify the meaning of that last, or add new information to that last word. And here's an example of another example of the word mole.
1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these, based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all three of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions as a function of the context. To take an
example, of course, of the riverbank in the financial institute, that's as we're moving it towards a more specific meaning of bank.
Another example is American shrew mole. 1 mole.
And then finally, we're going to go back to Grant once more.
More generally than just refining the meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially ones that are quite far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how, after all of the vectors flow through the network, including many different attention blocks, the computation that you perform to produce a prediction of the next token is entirely a function of the last vector in the sequence.
Wow, the last. So we're going to throw away all these calculations here. Wow.
So imagine, for example, that the text you input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model is going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word was, will have to have been updated by all of the attention blocks to represent much, much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word.
So it's not quite the end of the story, because we've got this this last vector, but we still got it. This is only established in our context. We still got it back to our neural net, the they are huge neural net and look at the probable next words. But then we're going to select the one given in this given context. But still, tremendous amount of calculation, matrix math, linear algebra, and the biggest benefactor, of course, of all this has been NVIDIA. And NVIDIA, who started life as a graphics card processor. And remember, but we can't forget, what is a GPU? A graphics processor is mostly matrix math. So these guys have always been really, really good at doing matrix math. So they deserve to have the position they now have as one of the largest computer outfits, because they can build these supercomputer centers of math processors. And these GPUs are really, really good at doing parallel computing. So not only can they do, they are the ultimate math processor, they are parallel processing engines, meaning they can run multiple logic paths at the same time. And so they identified this AI niche, and the AI was getting stronger back in 2015-16. So again, very astute. They made the right gambles, and they came up with their CUDA software. The GPU is just the graphics card, but you still have to have a classical programming model. And so part of the logic is going to work on a CPU, and this CUDA software is going to let the classic program, maybe in C, C++, whatever, fork and task to the GPU, and then wait for the result after the GPU. And of course, it can fork many of these at the same time. It provides the horsepower for most of the existing large AI farms. And there are huge ones. Look at the 100,000 GPU server farm that Elon just opened up down in Memphis, Tennessee. And this thing is 100,000 GPUs, and they're connected in their water-cooled units, much like I show here, but they're water-cooled, and it's so sensitive to power fluctuations, they had to put batteries in front. So the energy from the Tennessee Valley Authority goes first into these, and is stored into the huge Tesla batteries. Now, of course, Microsoft is going to respond, but the bottom line is huge power, huge energy. There's another interesting movement here, which is to these ASICs. An ASIC is an application specific, and it's moving the software into the hardware. Well, it's a huge gamble, because if you move the transformer logic right into the firmware, that's a single-purpose machine, and if things ever change, well, throw away the hardware. And of course, let's talk a little bit about, now the intelligence is one thing, but the power is another thing. There's been a 10 billion increase in the power requirements for AI. And which made case, and here we have Microsoft is buying into the 3 Mile Island project in order to revitalize it. And so we have a nuclear power plant that is going to be used just to train AI. Oh my God. And then, and look at this in particular in terms of the human brain. The human brain only consumes 20 to 30 watts. And it's about that would power a light bulb. And to train some of these new models, the Llama 3, the Grok, these things can take the net power equivalent to consume by New York and London combined. Now, so the power, and the question is, are these things really intelligent? There's O1, which is the new so-called learning or large reasoning model from OpenAI, And yeah, it does seem to do math really well, and scores well on math tests and science. And yeah, I think there is some signs that it may be doing some reasoning, but it's extreme. According to Francois Chalet, is that it's extreme sensitivity of large language models to the phrasing. If you change the names or the or places in the variable names in a prompt, you can break the LM. And he asks the question: to what extent do large language models actually understand something if you can break their understanding with simple renamings? Because it's performing superficial pattern matching rather than robust understanding. The large language model performance depends upon task familiarity, not task complexity. Now, and another thought here is, of course, does it reason? Well, that O1 looks like it's reasoning, but maybe it's just finding reasoning patterns in the training data. I think over time we're going to find this answer. Now, don't get me wrong, it's doing some amazing things, most impressive. But is it actually reasoning? I don't know. Now, and according to Francois, the improvements rely on armies of contractors applying fixes to the failed queries. And you can make a query, particularly in math, and it'll fail, and then suddenly in 2 or 3 weeks it starts working, because they have more than 20,000 humans involved in patching these networks. Now, and according to Francois, here we are. Here's a time sequence here. We have organized knowledge, and then the generalized models, and then on-the-fly model synthesis, and then we're moving towards AGI. And on this timeline, he says that large language models are mostly at this stage, somewhere between organized knowledge, because yes, they have tremendous amounts of knowledge, because they've gone out and grabbed all the knowledge of the web, including some stuff they shouldn't be grabbing. And they're able to do some generalization. But he says we're somewhere in between here. Now, if we can they generalize? If we solve most large language model limitations, the hallucinations, and that's the really bad one, particularly if you're dealing with things like medical applications, you don't want your medical application hallucinating. Brittleness and the generalization, we may be able to get here, but not tomorrow. This is going to, this is at least a few years, and it's a massive jump to get to on-the-fly model synthesis. And this, and of course, and the next, and this takes us to AGI, to the artificial general intelligence, which we may never get to. So, and what Francois says, well, learning, more on learning, we have system one learning, fast and automatic. Automatic, it's just as you ask, what's your name? John. You don't have to think about it. But in system two is slow and deliberate, where we solve complex problems. Transformers, according to Francois, transformers are a type 1 abstraction machine, and they're not good for type 2. And that he claims the progress toward system 2 and AGI has stalled. And we need a new breakthrough, especially given this huge power requirements and compute. It's just too darn expensive. And we look at, an MIT study shows that only 23% of workers' wages could be replaced by AI for less expenditure. And only the most mind-numbing and simple tasks are at risk. And yet we're expending all this energy and all this trillions of dollars. And even in these cases, we can only augment and not replace. The vast majority of jobs are safe now and for the foreseeable future. And those were the words from Francois, one of the premier AI researchers. And Jan LeCun, Jan is heads the AI development for Meta. Meta, of course, formerly Facebook, and he's one of the most influential forces in AI. He says we need machines with human level intelligence. Learn a model of how the world works through sensory input. So it has to remember from that sensory input and then be able to reason and plan. And he claims the current systems cannot. And the current large language model has the intelligence of a cat. However, a very knowledgeable cat. And we have to move to objective-driven AI. And this is a alternative to the reinforced learning. In RL, an agent learns by trial and error and through rewards. And this is more the traditional training we now do. It's terribly inefficient, as we've seen, requiring massive calculations. And these rewards are not always available. We have to shift towards predictive world models. The idea is for an AI to develop an understanding of its environment by predicting outcomes and using those predictions to guide its actions. So we get something to somewhere like this where we, let's just skip this. Now we reach a stage that there's another possibility here. It looks like we're, according to Francois and LeCun, we need something new. We need some novel thoughts, or else we're going to be stuck in another AI winter. But another possibility here is that the future might be the intersection of neurophysiology and computers. Because the brain, specifically the neocortex, is the organ of intelligence. Firstly, the biological neurons have little resemblance to artificial. In AI, a neuron is going to take all the inputs and process them from the previous layer. And this is based upon an old view of how the brain works. In the case of the brain, the human mind, the biological only looks at a subset. It's going to use context, which is derived from other neurons firing into it to decide to fire or not. So it's not always going to fire, and it doesn't depend. The context is going to determine that. And the majority of synaptic input does not make a neuron spike. It just makes it more ready to spike. It's going to put it into a prediction mode. And this is consistent with what the brain likes to predict and wants to stay in the state of low energy. It's going to form a world model. And from its sensory input, our touch, our sight, our hearing, and my model is going to be different from yours. And it wants to predict what's going to happen next. And if it's different from what it predicts, then it's going to, on the fly, change that model. So what a neuron looks like, the single neurons actually have complex computational devices. And in fact, some recent research claims that it's almost equivalent to each neuron is like a large language model. Now we get to Jeff Hawkins and Numenta. Hawkins, the founder of Numenta, interesting guy. He was the founder of Palm Computer, the Palm Pilot years ago, 2003. and he sold it to HP. So he is a a computer guy who took that money and he sold the company to HP, and he went back and did what he really loved, which was neurophysiology, and he founded Numenta. Now he has this Thousand Brain project. It's a platform for building AI and robotic applications using the same principles as the human brain. The platform represents an alternative form to a form of AI. Let's listen to what Numenta has to explain their own project.
Your brain. How it understands the world and creates intelligence is one of the most important questions of all time. If we want to know ourselves, and if we want to create intelligent machines, we need to first understand how the brain works. This part of the brain is called the neocortex. The neocortex is responsible for everything we consider intelligence: seeing, hearing, abstract thinking, language, arts, and science. It learns a model of the world in your head. The model recreates the structure of everything you know. Everything you do and experience is based on this model. Intelligence is the ability to create this model of the world. But how can a bunch of cells create a model of the world and everything in it? The thousand brains theory answers this question with a surprising insight. Consider a coffee cup. Neuroscientists used to think there was only one model of the cup. Since we can recognize the cup by touching it or seeing it, the inputs from the eyes and skin would connect to the single model of the cup. But when we look at the neocortex, it is composed of about 150,000 units called cortical columns, each about the size of a grain of rice. We now believe that each column independently creates models based on what it's sensing. Therefore, there are thousands of models of the coffee cup distributed among thousands of columns. Some columns get inputs from different parts of the skin. They model what the cup feels like. And some columns get inputs from different parts of the eyes. They model what the cup looks like. But then why does the coffee cup seem like one thing, not thousands of separate things? Some of the cells in the neocortex send signals long distances. They're like wires that go from the left side to the right side, from the front to the back. What these connections do was not known. The thousand brains theory proposes that these connections allow the different models to talk to each other. In essence, they allow the different models to vote to reach a consensus, a singular perception of what we are sensing at any moment. We're not consciously aware of what's going on inside each column, but we are consciously aware of the activity in the long-range connections between columns, so we are aware of the consensus reached by all of the columns. This is why we have a singular perception of the world. But how do columns actually learn models? The neurons in each column create something called a reference frame. A reference frame is similar to a map, or similar to the X, Y, and Z axes of coordinates. The reference frames in columns allow the column to represent the three-dimensional structure of the world. Everything we know, every fact and piece of knowledge we possess is stored at locations in reference frames. This insight resolves many profound mysteries of what it means to know something, how we see analogies, and how we solve problems. And it also tells us what we need to do to create intelligent machines. To date, we've managed to make machines that outperform humans on a few difficult tasks. But they are not intelligent. They cannot reason or learn about the world like we do. The thousand brains theory provides not only an explanation of how our brains work, but also a blueprint for how to build truly intelligent machines. These machines will think faster than we do, sense more than we can.
So I think you'd agree this is fascinating stuff. And let's just resume our so in summary, what just some of the thoughts here, that humans, of course, are different from today's AI. some points we learn quickly and continuously. And particularly, the important thing is continuous. But we're constantly updating our model of the world. As I said, we want to remain in the state of low energy. And AI must be fully trained before it can be deployed. And we do not have to undergo a lengthy and expensive training phase to learn something new. We're going to be able to apply what we learned in the past to a novel situation. Hugely different. We interact with the world and manipulate tools and objects in sophisticated ways that are going to leverage our knowledge of how things are structured. And what we think of as intelligence, from seeing to touching to hearing to conceptual thinking, is created by a common neural algorithm. It's in the neocortex. The mechanism is implemented in each of the thousands of cortical columns. We are infinitely more flexible as we learn these new skills. AI can be trained to beat humans in things like Go, but has no idea what Go is. And the question is, are we on a path to create truly intelligent machines? What we've done so far, does it qualify as intelligence? I think it's a big question mark. Or we are entering an AI winter as we have in the past. And in the words of Jeff, deep learning does not put us on a path to AGI. We need a new approach. So what I hope I just shared with you some of my thoughts on how the current our current models work, or some of the training, some of the math that is behind it, showing you that it's an exercise in matrix math, and some thoughts from some of these important people in the industry. But these are just my ideas. I mean, golly, I'm just sharing with some of the research I have done, and I hope to continue doing this, and because it's such a fascinating field. Thank you.